Hey everyone, I'm McCabe Levingood, and today I'm going to be walking us through Physics Lab 1 over constant velocity. We're going to go ahead and get started with an introduction. The purpose of today's lab is to observe the motion of an object that is moving at a constant velocity, meaning the object is moving at the same speed without changing direction. We're going to do this by comparing computational model observations to the experimental observations using physics principles. The physics principles we're going to be using are Newton's first law, which states that an object will remain at rest or in uniform motion unless acted upon by an external force. Newton's second law, which states that force is equivalent to mass divided by acceleration, meaning that an object's acceleration is dependent on the object's mass and the net force acting on that object. And lastly, constant velocity. This is a really key concept of today's lab. This just means that an object is moving at a constant speed in a straight line. The object is not experiencing any acceleration and therefore no net force during this time. We are going to analyze constant velocity today using the experimental method and the computational method. In the experimental method, a ball will be rolled across the floor at a constant velocity. The movement of this ball will be measured using tracker. The system is the object being observed or analyzed, and in this scenario, the system is the ball. The surroundings include everything else around the system that typically have a significant effect on the system. In this scenario, the surrounding forces are the normal force, gravitational force, applied force, and friction force. In the computational method, the position versus time graph was created using GlowScript coding. The results yielded very similar numerical values, and both methods showed a linear change in position and therefore a constant velocity. Calculations done in today's lab required these three formulas. First, we have the velocity update formula, then we have average velocity formula, and position update formula. Experimental method, a ball was rolled across the floor, as we can see in this video, and the position versus time was measured using tracker in the picture to the left. You can see that. At the bottom of the screen here, we have the graph that tracker created. It's a position versus time graph. As you can see, the position has a linear slope and it's increasing at a constant rate. This means that the velocity is constant. Over to the left, we have the points on the graph. In this method, we used coding to calculate the position of the ball over time. So first, in line 32, we have the ball's mass. We set it equivalent to 1 because the mass is in this scenario is not significant. Next, we have the ball's position. We set the x, y, and z components of the vector equal to 0 because the ball started at the origin. Moving on, we have the ball's velocity. The velocity was calculated using the average velocity formula, which is a change in position over a change in time. And the ball only changed position in the x direction, so the y and z values are still 0. Moving down to line 54, we plugged in the F-net values. In this scenario, as we've said multiple times throughout this video, the velocity is constant and therefore there is no acceleration and no net force, so all of these values are 0. And then down on line 58 and 60, we have the velocity update formula and the position update formula. Code led us to these two graphs. First, we have the position versus time graph, and then the velocity versus time graph. On the position versus time graph, you can see that the position increases as a linear function, and then the slope of the position function is seen in the velocity graph. You can see that the velocity is constant throughout. Experimental and computational methods were compared. As you can see, they're fairly similar. There are going to be some differences because in the experimental method, there was friction force acting upon the ball. On to the discussion portion of this lab. What if I were to flip the x axis, meaning movement to the right of the origin was negative and movement to the left of the origin was positive. This would be totally okay. In these scenarios, you can pick the origin and you can pick which direction is negative or positive as long as you stay with that consistently. So the position and velocity unit vectors would change in sign. However, the magnitude of the position and velocity would remain the same. So my observations can be predicted well by the computational model. When you set the net force equal to 0 in your model, is it possible for you to say how many forces are added together to give 0 net force in the case that you observed? This is not possible. There are pushes and pulls in all directions, and therefore we cannot know exactly how many forces are acting upon the object.